Okay, thank you very much for the invitation to the summer school and also to the conference. It has been a great combination of mathematics, language lessons, and tourism. I don't think I've seen so many churches in one day as I have here. So I want to say something about the, what was it, geometry and combinatorics. Of Wei Zhang's. Arithmetic fundamental lemma. In my valley, this year there have been two big avalanches. And even though this valley may be somewhat removed from the interests of other participants, I think it may be interesting to know about these two events. I will use the following notation. So P will be an odd prime number, and F is a finite extension of QP, and I take E to be the unramified quadratic extension. And then I also fix a natural number at least equal to 2, and I look at the following injection of GLN minus 1 into GLN, where I just ascend the matrix H to the block matrix. I put H in the first one and the middle one in the first block, upper block, and the one in the lower block. And then, of course, this group acts by conjugation. And this leads to the situation that we have in geometric invariant theory. And so we call an element gamma, we call regular semi-simple in the GIT sense if its orbit is closed and the stabilizer trivial. This has nothing to do with the usual notation of regular semi-simple. The usual notation of regular semi-simple arises by the conjugation action of GLN on itself. I mean, then it's an exercise. I think one can do this in linear algebra too, to show that regular semi-simple, in the sense that all eigenvalues are distinct, is the same thing as saying that the orbit is closed and that the stabilizer, in this case, it's not trivial, but it will be central. Okay? Okay, and now, so this is the situation, and now there are two things that one has to understand before being able to appreciate what I'm going to talk about, namely matching and transfer. So in some sense, these two notions are dual to one another. And I will start with matching. For this, I look at the following space. So let me actually write, one can write this as an algebraic variety, but I'm more interested in the F rational points of this algebraic variety. Namely, these are those elements such that gamma times gamma bar is equal to the unit element. So gamma bar means that I apply the non-trivial automorphism of E over F to all the entries of gamma. Okay, so this is one side. This is called the symmetric space side. And then there's the unitary side. So here we fix a Hermitian vector space with respect to this quadratic extension of dimension n. Now in the p-adic case, up to isomorphism, there are two such spaces, the split space and the non-split space. Split means that there is a width basis, non-split means that it doesn't have a width basis. And I would denote them by W0 and W1. So let W0, W1 be the two E over F Hermitian vector spaces of dimension n. W0 is a split space, and I also fix vectors, special vectors U0 and W0 and U1 and W1 such that they have the same length. And it should be not equal to 0. And then I denote by Wi flat the orthogonal complement of the line spanned by Ui. And then after choosing a basis, where I take as a first basis vector Ui, and then I complete it by some basis of Wi flat, I get an injection of the unitary group inside GLN. GLN, I mean, let me put it on rational points. This is contained in GLN of E. And similarly, the unitary group of Wi flat is contained in GLN minus 1 of E, of F, sorry. Contained in GLN minus 1 of E. Okay, and now I can say what matching means. Namely, we say that gamma which is regular semi-simple, regular semi-simple considered as an element of GLN E. This matches an element G inside U. Let me just call it Ui of F, regular semi-simple. This again just refers to this embedding here. If they're conjugate, under GLN minus 1E. Okay, so this matching gives me a possibility of comparing regular semi-simple elements in two groups. I mean, this is not really a group, it's a symmetric space, but into these two things which are completely different entities, subsets of this group GLN minus GLNE. Okay, and now comes the surprise lemma. This is due to Jacquet, which states the following thing. The matching relation induces a bijection between the conjugacy classes of Sn of f, regular semi-simple, and the disjoint union of the regular semi-simple elements in the unitary group U0 and the regular semi-simple elements in the group U1. So in other words, if I take an element, regular semi-simple element here, then it is matching exactly one element of either U0 or U1, which is unique up to conjugation. And conversely, if I start with an element of this unitary group, which is regular semi-simple, then it is matched with exactly one element on the symmetric space side up to conjugation. Okay, the proof is just linear algebra. So once you find this lemma, it's not so hard to prove it, but actually to find this lemma, I think, is pretty ingenious. Okay, now the next thing is transfer. This is in some sense dual because we are now going to look at functions. Okay, so let's start with the symmetric space side. So this is transfer. Symmetric space side. I look at the following weighted orbital integral. So I take a function, C infinity with compact support, on NS, Sn of f. And then I consider the following integral. So for reasons which will become clear in a minute, I will also introduce a complex parameter S, and then I form the following weighted orbital integral. So integral over GLN minus 1f f prime h inverse gamma h times eta of determinant h times absolute value of determinant h to the s dh. And when gamma is regular semi-simple, then this integral is convergent.
So you integrate over conjugate?
I'm conjugating here over the conjugate of gamma, but I'm also introducing this factor here. So in other words, this is not invariant under conjugation, but okay, it's not invariant under conjugation, okay? So now let's take the case which for the moment is the most interesting case where s is equal to 0. So this I call the weighted orbital integral. Then this transforms, so it's not invariant under conjugation. I should have also said, what is this eta? Eta is the quadratic character associated to this unramified extension E over F by local class field theory. Okay, so then this transfers under eta of determinant under conjugation by H. And therefore one introduces a factor, namely it's called the transfer factor. At the moment, it's not important how this is defined. Omega of gamma, which also transfers in the same way. And in this way, we see that if I multiply this, I mean, it's a quadratic character, so I multiply it with omega gamma, then this becomes a function on the conjugacy classes. So in other words, on Sn of S regular semi-simple.
So what you're doing, you take integrations for conjugacy classes here, and then what you do
I conjugate over this subgroup here, and here I do conjugation, but here I add this weighting factor. This weighting factor has to do with the fact that this is not a group, but rather we have this equation gamma times gamma bar is equal to 1. Okay, so at the moment, let's take S equal to 0, then we get this thing here, okay? This transfers under this quadratic character, eta of determinant. Okay, there's a transfer factor, which I will define later in a special situation, which transfers in the same way. So if I multiply this over the integral by this factor, then it actually is invariant under conjugation and therefore becomes a function on this thing here. Okay, so I have now a function on the left side of this identification. Now I want to define a function on the right-hand side of this identification, and this will just be an orbital integral. I mean, not weighted, but just an orbital integral. Okay, so for the unitary side, I do the following. Unitary side. So for function f, C infinity on ui of f, I define the orbital integral OG of f, and it's just the usual orbital integral ui flat of f, f h inverse g h dh. Okay? And now I say that this is what is transfer. I say that f prime is a transfer of a pair of function f0, f1, where f0 is a function on u0 and f1 is a function on u1. This means that for any gamma which is regular semi-simple, I have that omega gamma times O gamma of f prime. This is equal to either the orbital integral of f0 if gamma matches an element g in u0, and it's OG of f1 if gamma matches an element g which lies in u1. Of course, everything regular semi-simple, otherwise these things don't make sense. Okay, and so the first theorem in this, the first non-trivial theorem is that transfers always exist. This is the theorem of Wei Zhang. So for all f prime, there exists a transfer f0, f1, and also for all f0, f1, there exists a transfer f prime. Which is not so surprising, because here also the elements always match. There always exists an element which matches. Okay, and the fundamental lemma concerns now the situation when everything is unramified. So let me call this fundamental lemma situation. So we made already the assumption that the extension E over F is unramified. I will also assume that the omega is a canonical transfer factor. And it's very easy, namely omega of gamma is simply -1 to the valuation of the determinant of the matrix that you get by applying gamma to the basis vectors E1 up to En. Okay, so by applying gamma to a basis E1 up to N, you get a quadratic matrix of size N, you take the determinant, and this has either odd valuation or even valuation, and depending on this, the transfer factor is 1 or -1. And finally, I also take all these orbital integrals, of course, depend on the choice of a Hau measure, but there is a canonical choice of a Hau measure. On U0 of F, namely U0 is the unitary group for a split space, and for a split space this means that there exists a self-dual lattice, and you just take the stabilizer of a self-dual lattice. So you assume that the volume, you normalize the Hau measure by saying that the stabilizer of the self-dual lattice, which I call K0, has volume 1. And finally, I also assume that these special vectors, I just said in the beginning that they should have identical lengths. I now assume that their length is equal to 1. Okay, and under these conditions, the conjecture, which is called the fundamental lemma, conjecture states that the function, the characteristic function of the compact subsets that you get by taking integral matrices inside the symmetric space, that this matches the function that is equal to the characteristic function of K0 in the 0 entry, and it transfers to 0 on the non-split unitary group. Okay, this is a statement. And before I say what is known about this, so this is the first avalanche that went down the valley this year. Namely, this is a true statement. I want to make this statement explicit because it turns out that this is a totally elementary statement. Namely, okay, so calculations of both sides. No, how do I say it? I want to give the elementary expression for the fundamental lemma. Okay, so I start with this element gamma on the left-hand side. And I assume that it is matching an element on the split side. Okay, then the elements U0, so this is a special value in the zero Hermitian space, in the split Hermitian space, then G of U0, and so on, up to G to the n minus 1 of U0. This is the basis of W0. This is a consequence of the element being regular semi-simple. And I form the lattice generated by these basis vectors. Yes, this comes from regularity. So I form this lattice in W0 and I also define an involution which is antilinear with respect to complex conjugation, with respect to the conjugation action of E over F on W0 by setting tau of Gi of U0 is equal to G to the minus I times U0. Okay? And then you calculate these you try to calculate these orbital integral for characteristic functions. This is a general philosophy that I think starts maybe with Langlands, that orbital integrals for such characteristic functions are just the counting of certain lattices. And you just plug in this usual method and you get an identity. And this identity is the fundamental lemma. And it's very easy. So the fundamental lemma conjecture asserts the following identity, namely, you have here omega of gamma, then you take the sum over all lattices lambda inside W0, which are squeezed between the lattice L and its dual lattice, and which are fixed under the action of G, and finally, which are fixed under the involution lambda. And then here you just take minus 1 to the length of lambda modulo L. Okay? This is the left-hand side when you calculate this orbital integral. It's just a combinatorial identity, and the assertion is that this is the same thing as taking the sum over, and now I'm just copying the same kind of lattices. So all lattices lambda and W0, which are squeezed between L and L star, which are fixed under lambda and under G. And now this last condition that it is fixed under this involution, this is replaced by the condition that it is self-dual. And here the sign disappears. And also the factor is of course also there. Okay, so both sides are just obtained by doing some elementary manipulation of orbital integrals and measures. And the assertion, so the basic assertion is that these two combinatorial expressions are equal. So it sounds like a completely elementary thing. Why don't people just calculate this and show that they're equal? It turns out this is very difficult. Still, this is a theorem that was finally proved this year, that this conjecture is true. So theorem. This is true. Let me say something about the history of this. So the final version of this is due to Berzard-Plessis. And for P bigger than n, it's also due to Wei Zhang. His proof is different. But before this was proved by Ji-Wei Nguyen. So this is maybe 10 years ago. He proved this by following Ngo's proof of the arithmetic of the usual fundamental lemma in the theory of automorphic forms. So he proved this actually in the function field case, and then one can prove deduce this by means of logic for P sufficiently large but unspecified. So in some sense, the proof of Berzard-Plessis is the best because it gives the result in general. But there are some advantages also to the other proofs, so they should not be forgotten. And Berzard-Plessis' proof is completely elementary, but it uses Fourier analysis. It doesn't use this interpretation in terms of lattices. Nobody has so far found a completely elementary proof just in terms of lattices that would establish this identity. Okay, so now the next question is what happens if the element gamma matches an element in the non-split unitary group. So let gamma match an element in the non-split unitary group, well then we know that by this statement here, we know that the orbital integral of this characteristic function is equal to 0, because it matches the 0 function on the non-split unitary group. And so instead of this value of this was the value of this of this weighted orbital integral at s equal to 0, instead of this one, we look at the derivative. So let me call it O prime of gamma, F prime. Oh no, maybe too many primes, maybe delta O gamma. So this is d mod ds of O gamma F prime s at s equal to 0. And it's easy to see that this transfers again under this quadratic character. And so therefore we can look at this quantity omega gamma times delta O gamma of F prime. So this again is a function on the set of conjugacy classes of the symmetric space. And the question is, what is the value of this? This is the arithmetic fundamental lemma. And before I do this, let me calculate the left-hand side and the style of this identity here. Namely, the left-hand side is equal to omega of gamma. And then we have here the same sum as before on the left-hand side. The same sum as before. Except that here we have, in addition to this length, this minus 1 to the length, we also have the length. Again, this is very easy to calculate. So this is the left-hand side. The question is, what is the right-hand side? How can one compare this? What can one compare this with? Now, I think nobody will be able to guess the answer of this, because it turns out that this quantity has a very deep arithmetic meaning, and it's related to the intersection product on Rapoport zinc spaces. Okay, so let me explain what comes into the right-hand side. So for this, to simplify, let me just take F equal to QP. It works in general. I also use the notation that I used in my course. This is here the extension, the completion of the maxima extension, maxima and ramified extension of E, and I denote by F, which is just the algebraic closure of Fp, the residue field. Okay, and then I look at schemes on which the prime, on schemes over the ring of integers, so maybe I denote by O breve, the ring of integers of O breve. I look at schemes where the prime number P is locally nilpotent in the structure sheaf. So I would just write S and I look at unitary p-divisible groups. So a unitary p-divisible group, this is by definition a triple over S. This is by definition a triple x iota lambda, where X is a p-divisible group over S, where iota is an action of OE on this p-divisible group, and where finally lambda is a principal polarization on X, such that its Rosati involution is the complex conjugation on E, in other words, such that we have the following anti-commutation rule between iota and lambda. And we say that such a unitary p-divisible group has signature PQ if the following cut-width condition holds on the Lie algebra of X. So X iota lambda has signature PQ. This means that we have that the characteristic polynomial of any element A and OE acting on the Lie algebra is equal to T minus A to the power P and T minus A bar to the power q for all a in OE. Okay, so we are most interested in the signature 1 n minus 1. And there's a fact, there exists a unique p-divisible group. I mean, what do they call it? Unitary p-divisible group over f of signature 1 n minus 1. N here is the same number as before. Okay, and so then the theorem about which I talked in my course in the summer school is the following. There exists a formal scheme which I will denote by Nn over the formal spectrum of Obreve, such that its points with values in such a scheme S is the set of isomorphism classes of X iota lambda, unitary p-divisible groups of signature 1 n minus 1 over S, and where rho is a quasi-isogeny between the restriction to the special fiber of S this is a quasi-isogeny of height 0. And of course compatible with iota and the polarization lambda. And furthermore, this formal scheme is smooth of relative dimension n minus 1. N minus 1. So if n is equal to 1, which I excluded in some sense, then Nn is trivial in the sense that it's just the formal spectrum of Obreve itself. If n is equal to 2, then this is isomorphic to the formal spectrum of the power series ring in one variable over Obreve. And in general, for n bigger, this becomes non-trivial. So I discussed this in my last talk of the summer school. The underlying reduced scheme has dimension roughly n over 2. And it has a very nice stratification by classical delinealistic varieties. But it is by no means a trivial object. But still, I think we have the feeling that we understand this formal scheme a little bit. Okay. Then we get a morphism, which I will call little delta, from n minus 1. It's a closed embedding in the following way. So I have here the universal object which I call y. So this has signature 1, 0, and I take here, if I have this thing here, I multiply this with y bar. In other words, where I pre-compose by complex conjugation, because then this has signature 0, 1, and if I multiply this all together, this has signature 1, n. 1, n minus 1. This one here had 1, n minus 2. This one has 1, n minus 1. And I look at the graph. So this becomes now a closed formal subscheme of the product. And because this base is one-dimensional, you see that the dimension of this thing here is twice n minus 1. This dimension is n minus 1. So in other words, we obtain a cycle in the middle dimension. Now this is exactly the situation which we like, because now we can take an intersection product. Namely, we have an identification of U1 of f with a set of quasi-isogeny self-quasi-isogenies of xn, which again preserve iota and lambda, and therefore this acts on nn by precomposing this this framing rho by G. And so I can also form the graph of delta post-composed with this automorphism of G. Okay, and now I have two cycles in the middle dimension, and one can show lemma if I take this intersection product between delta and delta G. By this I mean the formula that is in SGA7. So in other words, you take the derived tensor product of the structure sheaves and take the Euler-Poincaré characteristic of it. This is finite if G is regular semi-simple. Okay, and the conjecture states that this is equal to minus this intersection product. And so let me state, this is the second avalanche that went down the valley, the theorem. Okay, let me see, how do I doing time-wise? Okay, I have 5 more minutes, so maybe I state this in a complicated way. So first of all, so this is called the arithmetic fundamental lemma. So the arithmetic fundamental lemma holds if, so first n is equal to 2 or 3. This is the original paper of Wei Zhang, and there's a simplified proof. By my former student Mihach. Secondly, it is true for arbitrary n if the element G is minuscule, minuscule means that this lattice L that appeared here was contained in its dual lattice lambda star, that this is killed by the uniformizer. So this is due to Rapoport Stiege and Zhang. But we had a hypothesis on the size of P, which was now eliminated by Hu and Li and Zhu. And now the biggest result, I think, is that this holds if F is equal to Q, QP, and P is bigger than N. Huh? Minuscule. Minuscule means that lambda star modular lambda, so this depends on G, that this is killed by the uniformizer. In other words, this is just the vector space, which makes it easier to control the lattices which are squeezed in between these two lattices. Okay, so maybe I finish my talk with a little anecdote. So this paper of Wei Zhang is not yet on the server, but he sent me a preliminary version, and I showed this to Scholze, and Scholze immediately said that we should go through this manuscript in our seminar. So I want to make some advertising for this kind of seminar. Our seminar is called Argos, has been going on for at least 15 years. So this just means arithmetic geometry over seminar. And so Mihaj and I made the program for this, and then we went through this manuscript in, I don't know, 10 talks maybe. And one of the crucial steps in the proof of Wei Zhang is to show that the right-hand side, this intersection product, is locally constant when you vary the element G and this special vector U. In other words, if you move this a little bit in the p-adic sense, these two things, that then the right-hand side doesn't change. And so in Wei Zhang's manuscript, this proof was actually very convoluted. And on the spot, Scholze went to the blackboard and he sketched a proof which makes use of his capability of work with enormously big schemes. Namely, he considers these p-adic spaces as schemes, which of course is very difficult to imagine. And I just got yesterday a manuscript by Mihaj in which he worked out this idea of Scholze's talk. And so this is a substantial simplification in Wei Zhang's proof. So I think it's a triumph of the idea of such a seminar to look at some interesting paper and go through it in detail, especially if one has such members in the audience like Scholze. But I think everyone contributed to the improvement of this manuscript. We sent quite a number of corrections and improvements, of course, of a minor nature to Wei Zhang, and so now we have even sent a major simplification of the proof. Okay, I think I'll stop here. Thanks.